Denise. Good evening, everybody. My name is Sir Jude, and today we will have our final review of our entire lesson last week, which are about scientific notation and the electromagnetic spectrum. So our first lesson last week was about scientific and standard notation, and I was shocked na this was the one that most students still have difficulty comprehending and grasping because this is the one that I expect to be the easiest to digest but at the same time kasi ito yung wala namang calculation, naglilipatan lahat tayo ng decimal point and we're just counting the number of decimal places that we move that decimal point. But all right, here we are again, and I'm here to give you not the entire uh what do you call this? Not the entire lesson about scientific notation. This is just a small portion of our lesson last week, but techniques on how to convert numbers to scientific and standard notation and vice versa. So let's start with numbers from standard notation to scientific notation. 0.96. So our goal is to always move the decimal point to the after the first non-zero digit. And in this case, it must be between 9 and 6. So therefore, our coefficient is 9.6. And then we write times 10. So 0.96 is a number less than 1. So I classify it as a very small number. So we move the decimal point one place to the right, but since it is a very small number, the exponent must be negative. Okay, number 2. So number 2, we have 7.895. And 7.895 is a number between 1 and 10. So as a consequence, the decimal point is already after the first non-zero digit, which is 7. So therefore, we don't have to move the decimal point anywhere. That's why the given number is actually the coefficient already, and then times 10. So since we didn't move the decimal point at all, the exponent will be 0. Number 3, we have 38,901. 38,901 is a whole number, and it is implied that the decimal point is right after the last digit. So our goal is to move the decimal point after the first non-zero digit, which is between 3 and 8. And that takes 1, 2, 3, 4, 4 decimal places to the left. So our coefficient is now 3.8901 times 10 raised to 4. And because this is a very large number, with an extremely high value compared to number 1, then therefore, we will use a positive exponent. So it's 3.8901 times 10 raised to positive 4 as it is. Now, so that's the end of part 1. We proceed to part 2. And our task is to convert the following numbers to standard notation rather. So let's start with 5.6 times 10 raised to positive 1. So when we have a positive exponent, we expect that that number will be very large, okay? Larger than 1. So therefore, we have to move the decimal point one place to the right. So when we move the decimal point one place to the right, it will now be found after 6. So this is 56. Okay. Second example under part 2, we have 4.43 times 10 raised to 0. So the number 0 tells us that we do not have to move the decimal point at all. So we leave with 4.43. And last conversion for tonight, we have 2.974 times 10 raised to negative 3. We have negative 3 as our exponent. And because it is negative, it's like dividing this number by 10 two times or 3 times. So we have to move the decimal point 3 times to the right. Sorry, 3 times to the left. So count with me. 1, 2, and then 3. So you have two vacant spots and uh you have to fill them with 0. So this number is now 0.002974. So I hope I was able to clarify the rules in converting numbers from scientific and standard notation. So all the rules that we establish in scientific notation will now be flipped when it comes to standard notation. So this is the last time that I'm going to talk about it. Review our video lecture about it. Review our practice on your own. All right, next. So let me erase my writings first. So part 3. In part 3, we must identify the component of the electromagnetic spectrum given their frequencies. So let's start. In identifying the component of the electromagnetic spectrum given their frequencies, you always look first at the exponent in the scientific notation. And then once you have multiple components with the same exponent, then that's the time that you have to compare now the coefficient. So exponent first and then the coefficient. So let's start with 6.03 times 10 raised to positive 14. The exponent is positive 14, and the components with positive 14 range from infrared down to ultraviolet. So because that's a wide range, we have to um, settle down with the coefficient, which is 6.03. So in those range, where does 6.03 belong? That belongs under visible blue. Okay, let me write the answer here at the right. Okay, next. 9.87 times 10 raised to positive 5 hertz. There's no actual direct frequency indicating uh, a frequency raised to positive 5, but in radio, its frequency range is below 3 times 10 raised to positive 9. So therefore, this frequency belongs under radio. Next, we have 4.76 times 10 raised to positive 17 hertz. So positive 17 again is not a direct exponent that is explicitly stated in the frequency range. But we know that the exponent 17 can be found in the range on the exponents between 16 to 19, and that's X-ray. Number 4, we have 5.42 times 10 raised to positive 30 hertz. If you notice, most of the examples so far, I don't give the explicit exponent and the explicit range when where that specific exponent can be found. That's because I want you to read between the lines and to understand the range each spectrum has. So the exponent here is 30, and gamma has a frequency range greater than 3 times 10 raised to positive 19. So all numbers with an exponent of 19, as long as it has a coefficient of 3.00 times 10 raised to 19 and above, then therefore this range belongs under gamma. Number 5, 8.61 times 10 raised to positive 13 hertz. Again, another indirect exponent, but the exponent 13 is found between the exponents 11 to 14, which means it belongs under infrared. All right, second to the last, 1.56 times 10 raised to positive 15 hertz. another indirect exponent, but it can be found between exponents 14 to 16, which is on ultraviolet. And lastly, we have 6.20 times 10 raised to positive 10. Right down to the very last item, I just realized that majority, except probably the first, almost all items except for almost all frequencies except for the first one are indirect. So 10 is found between exponents 9 and 11, so that this will fall under microwave. All right. So let's now proceed to our main agenda for today, which is unifying the pyramid formula that we used last week. So let me read this problem to you. So, a Tagbanwa nutritionist bombarded a cassava cake with a ray that killed its germs without destroying its edibility. The rays had a wavelength of 4.29 times 10 raised to negative 13 meter. Calculate the frequency and energy of the ray. So, remember that the first pyramid formula that we use has something to do between the relationship between the speed of light in vacuum, which is a constant, the wavelength, and the frequency. And the second pyramid formula that we utilized last week showcases the relationship between energy, Planck's constant, and frequency. So you might be wondering, do we always use the first pyramid? Do we always use the second pyramid in all calculations? I argue and I answer that it depends on the problem or the given presented to you. So in our case, based on the problem from the previous slide, the wavelength given is 4.29 times 10 raised to negative 13 meter. So because this is wavelength and the first pyramid has the wavelength, then therefore we must start our problem solving with the first pyramid. So I always start by writing the constant, which is in the first pyramid, it's the speed of light in vacuum, 3 times 10 raised to positive 8 meters per second. And then I now write the given value, which is 4.29 times 10 raised to negative 13 meters. So that means there's only one left vacant spot in the first pyramid, and that's frequency, the first value that we have to calculate. And based on the pyramid, you notice that the speed of light in vacuum is at the top and the wavelength is at the bottom. So therefore, we have to divide the speed of light in vacuum by the wavelength. So 3 times 10 raised to positive 8 divided by 4.29 times 10 raised to negative 13 meters, it will give you a frequency of 6.99 times 10 raised to positive 20 hertz. So at this point, no, I don't have to remind you again and again which buttons to press. In your scientific calculator, we have dealt with a lot of problems. We have utilized and employed a lot of scientific notations. So dapat alam na kung anong mga buttons na kailangan pindutin para makakuha ng accurate results. All right? So next, we have to look for the energy. Now notice that of the two pyramids, of all the letters in the pyramids, only frequency is the one that is common or repeated among them. So therefore, the calculated frequency that we have on the first pyramid will be directly copied to the second pyramid. And this is also the time that I will explicitly write the Planck's constant, which is 6.63 times 10 raised to negative 34 joule second. So before we use our calculator, now what operation are going to use this time with the second pyramid? You have the Planck's constant at the bottom left, and you have the frequency at the bottom right. They're situated next to each other, so you have to use multiplication. You have to multiply H by F, and it must give you an energy of 4.63 times 10 raised to negative 13 joule. All right. So even though we're already officially done, because I only asked for the frequency and the energy, no, let's use our values here to interpret nasa ang region nga ba ng electromagnetic spectrum si Wood irradiation chamber, no? So to answer that question, because we're going to use the frequency table and there are six values here, it will be confusing which number to pick, especially because we're dealing with scientific notation. And I would argue that because we're going to interpret using the frequency table, then we have to rely on the frequency, which are represented by colors green and orange. So technically, same, ano lang sila, same value lang naman sila. So remember, this is our frequency, 6.99 times 10 raised to positive 20. And here's a frequency table. So positive 20 is greater than the exponent 20 is greater than the exponent 19, which means that the food radiation chamber ejects or discharges gamma radiation. Now, so for our last lesson last week, gamma, do we classify it as non-ionizing or ionizing? So gamma radiation usually causes molecules to disintegrate, no? As I mentioned in the problem, it kills germs found in the cassava cake. So therefore, it has to extinguish the germs or microorganisms by disintegrating them. So gamma is considered ionizing. And there you have it. This is how we solve problems using the two pyramid formula. Now, let's proceed to our seat work a while ago. So not everybody was able to answer the seat work on time. I facilitated the seat work in a way that not only that you have to answer it completely, no, that you have to consider also the time. So basically you're competing not only with yourselves but also with your classmates, no? And I was this the activity that we did a while ago was sort of an a refresher or like a preparation for your performance task 2.1 tomorrow, which as I showed you this morning is over 175 points. But don't worry because it will be accomplished by group. So whatever we did in this review will also be repeated tomorrow, but with different scenarios, problems, and obviously different values as well. But anyway, let me just cut to the chase. So our carpenter tries a 15-minute sauna therapy to soothe his back pain. The radiation discharges an energy of 2.29 times 10 raised to negative 20 joule. Calculate the frequency and wavelength of the radiation. Identify what region of the electromagnetic spectrum the radiation belongs. And classify whether it is non-ionizing or ionizing. So, remember, our given value is 2.29 times 10 raised to negative 20 joule. That is joule. Palitan ko lang. Ayan, sorry for the long pause. That should have been joule instead of meter. So because our given value is energy, then therefore we must rely on the second pyramid formula. So I put the Planck's constant first, 6.63 times 10 raised to negative 34 joule second at the bottom left of the second pyramid. And then energy, 2.29 times 10 raised to negative 20 joule. So to get frequency this time, you have energy at the top and the Planck's constant at the bottom. So what do? We divide them. So we divide energy by the Planck's constant, giving you an energy of, sorry, a frequency of 3.45 times 10 raised to positive 13 hertz. Now, the next property that we must calculate is the wavelength. So we know that frequency is the only repeating quantity in the both pyramids. So we have to copy directly the frequency that we solved a while ago. And then the constant now is the speed of light in vacuum, 3 times 10 raised to positive 8 meters per second. So we have wavelength as the last entry in our pyramids. So to get the wavelength, we have to divide the speed of light in vacuum by frequency. 3 times 10 to positive 8 divided by 3.45 times 10 raised to positive 13. That will give you a wavelength of 0.000000870 meter or 8.70 times 10 raised to negative 6 meter. Now, after we completed the pyramids, we have to identify in what region of the electromagnetic spectrum does the radiation emitted by the sauna belongs to. So remember that in the frequency table, we only rely on the frequency, 3.45 times 10 raised to positive 13 hertz. And we have this frequency range here. The exponent 13 belongs on the exponents between 11 to 14, meaning that solar radiation emits infrared. And lastly, infrared is considered non-ionizing. It mostly causes vibration of molecules. Nothing bad really happens when it comes to non-ionizing radiation. But then again, no, it depends pa rin as well. It's generally safe, but of course, no, excessive exposure to infrared radiation in the sauna can cause you probably burns, blisters, and other skin diseases. It may affect your body as well. There's the reason why we always have limits, no? Because at some point when you exceed them, they will become harmful for your health. So why is it that we calculate the frequency, wavelength, and energy of the electromagnetic spectrum? So honestly, I, I have no, as a science teacher, I really have no idea. Aside from the fact that it's required that you solve this like literally, because it's not as if we wake up in the morning and we solve for this tree, no? But however, the reason why we do is because remember that each component of the electromagnetic spectrum has a different level of safety, no? Some of them are non-ionizing, some of them are ionizing. And there's a reason why iba-iba yan ang frequency range. There's a frequency range na safe, there's a frequency range na unsafe. So, regardless whether ibigay ko sa inyo yung wavelength or energy, no? Frequency kasi yung ginagamit natin sa pag-interpret ng component ng electromagnetic spectrum. So, I think that as shallow as my answer would be, no? Each, maiba lang yung number, maiba lang yung exponent, maiba lang yung coefficient, iba na ng electromagnetic spectrum, iba na yung magiging epekto niyan sa katawan natin. And that's it. So tomorrow we will have our performance task 2.1 by group. Print the printables that I ask you to print, and then bring your scientific calculator and pencil as usual. In the meantime, this is Sir Jude. Good night and goodbye. See you tomorrow.